And now let me welcome here my former colleague from Kokoi Observatory in Budapest, Robert Szabó. He is the deputy director of the Kokoi Observatory and probably the next director of this institution. And he will continue in speaking about space photometry and the revolution that it brought.
Thank you very much. Thank you for having me here. It works. So I'm going to talk about space photometric missions, especially about Kepler and about the micromagnitude revolution it brought us. Originally, I was thinking about talking about variable stars. That might be interesting for you. What happened? Okay. The good news is, or bad news, it depends, is that with that kind of precision, when we are talking about ppms and which translates into micromagnitudes, all the stars are variable at some level. So it's very hard to find constant stars. Actually, I know people who were looking very hard in the Kepler sample of more than 150,000 stars and could come up only with a dozen or something like that. It wasn't very quiet stars. So in principle, I could talk about anything or other stars, but I will restrict myself and I focus mainly on classical pulsating stars, RLI and Cepheid. And Gerard has just shown a very nice example of a lot of other variable stars, so I might skip a few slides. And my plan was also to finish with TESS, but Gerard was first and he talked a lot about it. But really, that's the future. So I'm going to focus about the Kepler and K2 mission and sometimes mention CoRoT and other space missions. But really, it is really thanks to Kepler that this kind of revolution came, not only in the exoplanetary science, of course that was the main motivation, but in the meantime, stellar astrophysicists are also very happy because of these missions. And there are very, very nice synergies between these two. So I summarized here the three most important characteristics of these missions that enabled this kind of revolution in science. One is this extreme high precision, 10 to minus 5, 10 to minus 6 in relative photometry. And the other interesting point is, and the very important one, is the quasi-continuous observations for months, for CoRoT, K2, TESS, and even up to years, up to 4 years in the original Kepler field. And these missions are able, most of them at different levels, but for example, Kepler was able to observe a large number of targets simultaneously. About RLI stars, these are well-known objects known more than 100 years ago. They were discovered more than 100 years ago, and they are showing large amplitude variations with a period of a fraction of a day, up to 1 day. And they come in different flavors. Some of them show constant amplitude variations, just like here, the upper panels. Okay. The lower panels, you see the well-known Blaschko effect, which is an amplitude and phase modulation of stars. And these are excellent distant indicators, well-known. Okay. And we like them to use as galactic structure tracers as well. So up to the advent of CoRoT, Kepler, and space missions, we thought they are boring objects. Actually, I was told by one of my senior colleagues that what are you going to see with Kepler and K2 and CoRoT in these stars? These are well-known stars. We understand their pulsations. And yeah, we were in the phase of target selection and preparation, because just for Bright, for Kepler, we had to pre-select the most important targets because it couldn't download all the full-frame images. So this is just one example that came with the first Kepler data. On the left side, you see RLR itself, the eponym of RLR stars, is the brightest one. And on the left side, you see a coordinated ground-based campaign organized by Kathleen Kohlenberg during one observational season for RLR. And you see the nice Blaschko modulation of about 40 days. But you can also see that despite having 5 or 6 different locations spread around the globe, there are gaps, and you also see the Fourier spectrum below, and you can compare it to the right side where the first few months of Kepler data came in, and I have to emphasize here, you don't see that each data point is more than 1,000 times more precise than the ground-based observations, and you can see the huge change in the Fourier spectrum as well. So, yeah. So before the Kepler data, I would say the Corot and Kepler data, RLR stars were thought to be monoperiodic, simple things, showing radial position, showing simple lighters. Some of them show a Blaschko effect, or Blaschko modulation. That's what we thought, that's what we found. And also the Blaschko effect was thought to be quite simple, just a sinusoidal modulation or something like that. But that completely changed with the space photometric data. Now we know that these stars are multi-periodic. They do show radial and non-radial pulsation, which is a good news if one wants to do seismology. Actually, they show complex light curves, quite frequent Blaschko modulation, and the Blaschko effect itself is quite complex. I will show a few examples. Here, this is the Blaschko zoo of the Kepler data. So you see the modulated RLR stars, are 80 stars actually. You can see quite long modulations in the upper panel with 2 years of modulations, and you can see small modulations, large modulations. You can see regular ones, and you can see highly irregular ones. So it turned out to be that this dynamical thing, this modulation is not as simple as one would thought. So it's pretty clear that it cannot be a simple geometric effect or something like that, because you see it changes from cycle to cycle. So it can't even be connected to the rotation of the star, as many of the theories previously thought that it has to do with the rotation of the star. It cannot be the case because it changes from cycle to cycle. Sometimes 42 days, sometimes it's 39 days. So it simply cannot be the stellar rotation. And sometimes these stars go crazy at the minimum where the position is suppressed the most. And at the Blaschko minimum, you can see that the light curve shape doesn't even seem like an RLR star. So this one was almost accidentally discarded for the Kepler target list because we thought that hey, it's not an RLR, it's something else. But it is a very heavily modulated, extremely modulated RLR star. Another interesting thing is that among the RLR stars, and now I'm talking about RRC and RRD stars, those that show position in the first radial overtone. Almost all of them show additional modes when you go to space and have high precision photometry. And it's very characteristic. It comes with a very well-defined period ratio of 0.61, 63. And you see many of those in the oval sample, for example, from Gauss-based observations, many of them. But if you go to space, you see this kind of additional, very low amplitude modes, millimach amplitude modes in all of them. So it's a very good indication, very strong indication that in most of these stars show these additional modes. And most probably, these are non-radial modes. We are not quite sure yet, but there are a lot of investigation in this direction. Another unexpected discovery is the period doubling of Array-Lyrae stars, in Blaschko-modulated Array-Lyrae stars. What I'm showing here on the left is 65 days, 1 minute cadence Kepler data, short cadence data containing more than 90,000 data points. And you don't really see the individual pulsation cycles. What you see is the 40-day Blaschko modulation. And if you zoom in, especially in some sections, in some parts of the light field, you do see a very characteristic variation. This is period doubling. It's well known from nonlinear dynamics. It is this kind of thing that you have a large maximum, a large amplitude cycle, and followed by a smaller one, and again a large one, a small one, a large one, a small one. And if you can read off the labels, in some cases in Array-Lyrae stars, this difference between the consecutive maxima exceeds 0.1 magnitude, which is a huge effect. It's amazing that despite more than a century of observation, no one had ever seen anything like that. This is a bright star, 7 magnitude star. You take it binocular and you could see 1.1 magnitude difference. I started as an amateur astronomer. I don't realize that you can see 0.1 magnitude. But you have to go to space because this star has a period of about half a day. So if you observe one of the cycles during one night, then you lose the next one and you won't notice anything. So that's amazing. And it's important because it's, if you are familiar with nonlinear dynamics, period doubling is the route from regular dynamics to chaotic ones. So it's a very important dynamical phenomenon, and we investigated this quite heavily using numerical hydrodynamical simulations, and it turned out to be a result of a 9-to-2 resonance between a fundamental mode and an unexpected, very unsuspicious ninth radial overtone. It's a very interesting interaction between these two modes, and it's even more interesting that there were claims, and there were investigations actually based on mathematical computations, that this kind of resonance between the fundamental and the ninth overtone might be able to cause the Blaschko modulation itself. Needless to say, the Blaschko effect is still a mystery after more than a century after its discovery. But it was a very nice thing that we found something. We found a new phenomenon, the period doubling, and it was found only in Blaschko stars. So that was a strong indication that it has to do something with the modulation. We also checked down to micromagnitude precision of Kepler, the non-Blaschko stars, and none of them showed anything like that. But many of the Blaschko stars do show period doubling. So Zoltán Kollát and Robert Buchler came up with this idea that the very same resonance that caused the period doubling, which is very nicely seen in Kepler, and also we checked in Corot and K2 and in other missions as well. So this very same resonance might be the culprit and might cause the Blaschko modulation. But it was a mathematical theory. It has to be demonstrated by hydrodynamical computations. And that's what was claimed a few months ago in September in France, where my former supervisor Zoltán Kollát announced that he found this kind of model. So his hydro models now show the Blaschko modulation. So it's a very important thing. I'm a bit suspicious because Blaschko modulation is very, very frequent. So this kind of mechanism has to work in a broad range of stellar parameters, which it's up to him. So he has to demonstrate that it really works. But this is the most plausible explanation. This kind of high order resonance, 9-to-2 resonance. At least I have to say that it's far more plausible than anything else that we have heard about in context of Blaschko. So that was a very nice starting point to see new phenomena, and we might even find something which might be the answer for this century-old enigma. But the Kepler mission came to an end, and because of these reaction wheels, actually, there were 4 of them on board Kepler, and 2 of them failed. And after that, Kepler couldn't continue what they observed the very same field in the summer Milky Way. But now there was another mission conceived, and I was lucky to be in California in 2013 when Steve Howell announced the new life of Kepler, which he called the K2 mission, and it became also a more than 4 years long mission. The Kepler just ran out of fuel a few weeks ago, and it stopped working. It had a wonderful mission for 4 years, from 2009 to 2013. Then there was some gap, while scientists and engineers were thinking about how to revive Kepler. And from 2014 up to a month ago or so, it had a wonderful mission on K2, which was steering along the ecliptic plane and observing given fields for up to 3 months. And the most important difference between Kepler and K2 was that it was no longer a very strongly focused mission, so it was a community-driven mission, and you can see how many papers were published on very different stellar astrophysics, and of course exoplanet characterization, a lot of other things, supernovae, microlensing, seismology, clusters, stellar activity, and so on. We also, for example, for RLI stars, we have a K2 RLI survey that we call, and you have to remember that in the original Kepler we had 50 RLI stars, and now in the K2 survey we already have more than close to 5,000, so 2 orders of magnitude more RLI stars, and in very different galactic fields, even in globular clusters, even in extragalaxies, Sagittarius streams, so very different environments. And our intention is to use this kind of Kepler-like data. So in K2 we do have the photometric precision, which is almost like Kepler's. So there are some technical problems, but we could reach this kind of micromagnitude precision, a few micromagnitudes. But the interesting thing is that we can use this survey, and we are in the process of analyzing all these K2 RLI data to investigate the occurrence rate of these newly discovered dynamical phenomena, resonances, the Blaschko modulation, period doubling, and so on, and also their dependence on the galactic environment, location, metallicity, and so on. And there are very nice synergies with Gaia, SST, and some other ground-based and space-based missions. We have nice light curves from K2. I will skip one of those. This is an interesting one. This is an RRD star pulsating in the first overturn and the second overturn, and both of the modes are modulated actually. So it's a doubly modulated RRD star. And the interesting thing is the amplitudes are anti-correlated. When one is low, the other one is high, and vice versa. It's still ongoing, and we are very close to submitting this paper. Marek is also on this one. This is the first batch of close to 600 RLI stars. And the interesting thing is that our at our homepage at Konkoly Observatory, we already published a lot of cleaned light curves. So these are kind of textbook data. It looks like if someone was generated with a plotting program or something like that. But these are real data, and real continuous data at very high precision for RLI stars, for modulated ones, non-modulated ones, RRC stars, Poro stars as well. And the K2 data will go into this database as well. RLI stars, there are a lot of meetings already, and there will be some announced that I'm aware of. That's another one. A little bit less than 1 year from now, we started to organize, actually 4 years ago, a series of conferences, and now it's the third part will be in Cloudcroft, New Mexico. If you are interested, you are more than welcome there. And I will switch to other type of stars very quickly, as I'm running out of time. We also had very nice observations on not only one Cepheid in the Kepler field. This is again, these are observations, very highly dense observations, and this is not. These are real observations of a Cepheid. Actually, most also observed, and Koro observed a few of them, 7 of them, something like that. This one is a very innocently looking Cepheid, but we found some long-term modulations as well. So it's also very interesting that it seems to be quite stable. So we are using them as distance ladder distance indicators, and they are very low amplitude things that's going on. So there's, for example, 150-day modulation in this kind of things, and we even found some extra signal in the Fourier spectrum that might be the sign of granulation of these large giant objects. Gerard has already told us about stellar seismology. I just want to show a few slides about this. He also showed how accurately one can derive stellar parameters, radius, mass, and age from stellar seismology. This is from the Sun, and this demonstrates the power of seismology, which it was started in the 70s actually for the Sun, and but now with Kepler, Koro, K2, and TESS, it is possible to apply the same techniques to distant stars, and that's really interesting. Here you can see the sound speed, and actually that's the deviation of the sound speed and the density of the Sun, stellar models, solar models, and the observations, and the deviation is only a few percent or less than that, so it's very powerful. And on the right hand side you can see the rotational rate of the Sun, which is enabled to derive by the stellar oscillations. And you can see that inside is rotating like a solid body, and you can see the well-known differential rotation on the surface of the Sun. The interesting thing is that you can see a very nicely structured spectrum of these stellar oscillations, solar oscillations, and stellar oscillations. And what you have to do basically is it's quite simple. There are very characteristic separations or frequency differences between different orders of frequencies. Now we are in the frequency space. You can see amplitude versus frequency. And one of these separations is it goes with the stellar mass, and the other one goes with the stellar age, and that's very important. That's because the other one, the small separation, is sensitive to the chemical composition inside the stars, to the center part of the stars. So it means that we have information about the stellar ages. And here is one example where, fortunately, these two samples that we were talking about overlaps. So they are the stellar, the exoplanetary host, and the seismology sample. And when we do have observations, seismological observations about exoplanetary hosts, then you can come up with nice results like this. This is Kepler 444, which is an M dwarf actually. So it's a star which is smaller than the Sun, but it has 5 rocky planets with quite short orbital periods. And the main importance of this planetary system is its age, which is coming from seismological observations. And the age was determined to be more than 11 billion years, which is more than twice as old as our solar system. So 2 important points. One is that there has been already stellar planetary formation going on along with the stellar evolution back at the dawn when our galaxy actually was formed. So it's the first or second generation of stars actually, if we don't take into account the hypothetical third population of stars, the very first ones. And the second important thing is that we think that this planetary system has been evolving quietly for more than 11 billion years. So if you are looking for places in the universe where life can evolve without major impacts and major catastrophic events, then that's a good place to start with. I think I have to skip a lot of other things here. I will show one eclipsing binary here, which I think it's quite amazing that in the Kepler sample we found something like that. So this star used to be an eclipsing binary, and during the observations in front of your eyes, it just stopped to be an eclipsing binary. It's not that unique. We have seen something like that from ground-based observations, but now you can see the whole thing as it is going on in front of your eyes. And of course, it's not a simple eclipsing binary system. There should be a third body in the system that made it to change its orbital configuration, and that's why as it changes, originally we have been in the plane, very close to the plane of this system, and now we are out of this plane. It's just amazing. Gerald has already talked about the heartbeat stars. I will just flash a few other slides. It's very interesting that Kepler already at K2 in particular observed galaxies as well in order to see supernovae as they are exploding. So literally they could catch the very first moments and continuously, which is extremely hard from ground-based observations. Usually what you see and what you discover is there's an already ongoing explosion in galaxies. And now here there's an example of a type 1a supernova which shows some extra heating at the beginning, at the very, very beginning of its life that was not possible to see from ground-based observations. The similarly interesting thing in a core collapse supernova type 2, which we call the shock breakout, that was predicted long ago from theory, but now Kepler was able to capture it in an actual supernovae. And there are light curves of active galactic nuclei and also cataclysmic variables, a lot of other things I am not expert of, and I'm going to show only just a few light curves. Just for fun, if you are observing about the rest and observing cataclysmic variables, this is just amazing. Again, you see these completely continuous light curves of very, very different objects. Even it turns out that, for example, the Pleiades, the brightest stars of Pleiades were observed in K2, and all of them show some kind of variations, which is also just amazing. And it's a technical challenge to observe these bright things with K2. And I will stop here. I just like to say that the fun is going on. So we are, as Gerard said, we are expecting the first publicly available test data, and so there's a bright future in space photometric missions. And with that, thank you for your attention.